This video is going to be a little bit of a deeper dive into Numpy for folks who want to know a little bit more. So what I'm going to start off here is I'm going to start off by recreating this ndarray using arange with 24 elements. And I'm going to reshape it to be 6 rows by 4 columns. Again, a 2D ndarray we can think of in terms of rows and columns. And that's what it looks like. Now recall that Numpy ndarrays are built to be multidimensional. So we've got this shape attribute, not a method, that returns the sizes of the dimensions as a tuple. So in this case, again, we have 6 rows and 4 columns. Now there's also a size attribute, and this is the total number of the items in the ndarray across all of the dimensions. So again, as we saw up here, 24 elements. Now we can use the npprod function in the Numpy module, and if we pass it shape, then it will take all of the values in shape and multiply them together. And this is interesting because the product of the sizes of the dimensions will always equal the size of the ndarray. All right, let's take another look at M so we can see what it looks like again. And let's talk about indexing. So I can index into a multidimensional ndarray. And again, for a 2D dimensional ndarray, we can think of this as indexing the rows, or at least the first dimension is indexing the rows. So if I say M sub 1, that's going to return me the second item in the first dimension, which is going to be the second row of this matrix. And I can go even further. So I'll chain another index operator to this, and this will get the third item in this row, which would be 6. Now, if you're looking at this, you might think, hey, this isn't much different than indexing into a nested Python list. And you're right, syntactically it's not. Let's take a look at another one. So let's take a look. Arange again, and let's do 24. And this time I'm going to reshape it into 3 dimensions. If I want to get the last element, the last value, 23, I can do that with indices 1, 2, and 3. Now it'll return me 23. But notice that the higher we are in dimensions, the more of these inner brackets we're going to have, which are kind of like syntactic noise. So Numpy, knowing that we're going to want to do this a lot, has introduced some syntactic sugar for making this much cleaner. And all you do, you just use one set of square brackets, and then you put commas in between the indices. So as you can see here, this cell and this cell are equivalent. And from our example before, for the other one, the other ndarray, 1 and 2, would return 6. Let's look at slicing. So I'm going to create another ndarray here, np arange 10, multiply it times 2. And that's what it looks like. And I could slice into it using the same syntax as I could for a Python list. Now let's look at multidimensional slicing. So again, here is our 6x4 M ndarray. And of course, if we saw before with indexing, I can get just a single row, or I could use a slice and get multiple rows. And that same syntax, that same syntactic sugar for slicing into multiple dimensions works. So I could say from this slice here, these 3 rows get the second and third value out of each of them. Now, here's where slicing starts to get really interesting. Notice that if you take a slice that has neither upper nor lower bounds, so no bounds, it's going to return the entire array. So you can think of this as saying that a slice without bounds in a single dimension returns all of the values in that dimension. You can still slice higher dimensions. So this is saying in the first dimension, or the rows in this case, select every row. But in the second dimension, select only the second value, index 1. And if you look at this, you're going to notice that this is basically the second column of M. Now you can also assign to a slice of a matrix. So let's see here. Let's say NP A range of 16 this time. And we're going to reshape it to be 4 rows by 4 columns. Then I'm going to take just the inner elements, the inner 2 elements, the inner square there, if you will. And I'm going to assign it a new ndarray. So this ones function, it will return an ndarray of all ones of a certain shape. And in this case, that's going to be 2 by 2. Let's take a look at what this looks like. So as you can see here, these inner values here are all 1, while otherwise we have the values from the arange function. Now, keep in mind that the source and destination have to be the same size. So if I tried to take that exact same slice and 1, 3 again, and this time assign it a 3 by 3 ndarray, it's going to tell me I can't do that because they're different sizes. Let's talk about one more interesting feature here. Let's say that we want to have an ndarray of starting at 0, ending at 10, with values at every quarter. So I could do something like this because the arange function accepts the same values as the built-in range function in Python. So I can say 0, 10, and then a step of 0.25. And this is what we're going to get. Not quite what we expected, because the upper bound is exclusive in a range and in an arange. So I'd have to do this to get that upper bound. Now there's also another function in Numpy called linspace that is designed to do exactly what we're talking about here. Linspace will take an upper bound and a lower bound and an upper bound, but this time the upper bound is inclusive. So the upper bound will be included. Then we just say how many values we want in the ndarray, and it will figure out the interval for us. So if I say 40, notice we get what we wanted, but we expected to be these spaced evenly at quarters. Well, that's because in order to do this, I have to add one to the number of intervals, and then I get what I want. So 2 ways to do basically the same thing. And before you think, well, there's not really a whole lot of difference here, think about it like this. Let's say we want to plot a sine curve, and we will actually do this later on in the sections on visualization. I can use linspace, and I want to plot this sine curve across the period 0 to 2 times np pi. And I want to plot it at every single degree. So that means I'm going to want 360, and then I add 1 extra for the endpoint, for the upper bound. And this is what I'll get. So I don't have to compute all of these. It figures out the intervals for me. So now what I could do, that would be my x values, like I said, my y values, np.sine. It expects an ndarray. Actually, that's lowercase x. And then if I were to say list zip xy, it's going to be a little bit noisy, but you'll see those are the points for plotting the sine curve. So that's all for the bonus video on Numpy. we now return you to our regularly scheduled workshop.